My introduction, Ian. So I'm just going to give a brief outline of my PhD project. So my PhD project has been like a three-pronged approach looking into resins for wind turbine blades and potential improvement in cure processing. So I've looked at characterising three anhydride cured epoxy resins. I've then taken this to look at interface between the resin and the fibre and how we can improve this, and then looking at vascular curing as a potential method to improve curing of thick composites which you find in wind turbine blades. So for the resins, I've characterised three anhydride cured epoxies and compared this to an industry standard. And we've looked at the effect of the anhydride structure on the resulting resin properties, looking at TG, modulus, thermal degradation, and also modelling the cure kinetics. If you're interested in any of this, you can come and find me at my poster. I've talked about the results before, so just want a quick overview at this point. So I then looked at resin interface. So at the minute, the resin's on glass fibre. So I should take a step back. Hold on. I did 3-point bend, short beam shear, to look at interlaminar shear strength, and we found that the anhydride resin is better than a industry standard amine cured epoxy resin on glass fibre. And although the amine does show increased toughness, we're not looking at that at the minute. We're looking at our improved, interlaminar shear strength. And the reason we think it's behind this is the fact that the interfacial bonding will be better. So now I'm looking at interfacial properties. So I've developed the Microbond test procedure in-house for use here with a machine that we've bought, and looking at developing the test parameters for that. And I've had good results so far on the resin, on glass fibre, and I've got the parameters I think now working. Just need to, sadly, also run out of time to get my industry benchmark value for this conference, but that is underway. But we're seeing good interfacial shear strength for the resin on glass. So then vascular curing. So we're looking at the manufacturing of thick composite parts. So if you've got a thick composite, you end up with issues from variation in cure profile, with thermal gradients through thickness, resulting in temperature lags and spikes, which would lead to residual stresses which create manufacturing defects such as warpage and cracks and delamination. Previous work here at the University of Bristol looked to model using vascular curing as a potential way to increase homogeneity of cure and the potential for multifunctionality post-cure. So, as part of the PhD, I've then looked at the experimental setup, so how we implement vascular curing in experimentally within thick composites, and we've had some really promising results so far. So I've been able to show that we can reduce the exotherm of cure and increase, put the heat into the cure quicker. So hopefully we can look to optimise cure cycles and show whether we're able to improve this residual stress. So future work, from my promising interfacial shear strength results on glass fibre, a big area for the industry is to move towards carbon fibre composites. So we want to look at moving the resin into a carbon fibre system and whether sizings can play a role in improving our interface. And also the vascular curing, so I've done 25mm trials, 50mm trials are currently underway, and we're looking at whether we can validate the model against the experimental results and then use the model to optimise cure of more complex geometries and prove this experiment. Thank you for listening to the presentation. Oh, hold on, should probably say thank you. I'd like to thank Hitachi Chemical Company for their support and the CIMComp hub. Also for Yusuf and Matthew, who did the modelling for the vascular cure, and I've had two third year final year undergraduates helping me the last few weeks, so Harry and Sarah. So thanks for that.